insulator. And what? Okay, nothing will happen. It's a salt. It's just sitting on the crystals, sitting on the surface. The insulator string always has some safety margin. Not much will happen. If in one nice morning fog will come, or light rain, or something like that, that's a disaster. Because then you have the moisture which is absorbed by this layer, and then it creates kind of solution like emulsion or something like that, which is conductive. And then you have huge leakage current flowing through the creepage, passing through the creepage distance, actually creating more or less kind of semi-conducting material which just short circuit the insulator. So this is the problem. So environmental impact of this type, temperature causes U formation on insulator surface, especially when sun is going down or another way around. Humidity, rain fog. Heavy rain is useful because then it washes the insulators. But light rain is not really good. So that's how the surface of polymer insulation look like. Silicon rubber. You see, it's droplets. In glass insulators or ceramics or porcelain, it's usually covered with the layers of water. But for silicon rubber, is this solid solar radiation. It's aging for polymers. That's for sure. Ice and snow. That's how this could look like. Very typical for Canada, especially in North territories, where when the complete line just covered with tons of ice. They have huge safety margins for insulated chains in this case on the nose. Wind, transport and deposition of moisture. Yes. Lightning causes flash over. These are weather conditions which may affect the insulation performance output. Pollution flashover. Just very quickly, I will not tell much about this because time is. So it's all about leakage current and creating conductive layers. May appear under operating voltages or over voltages. That's also may be the factor. Insulation strength depends on the materials. Usually, yes. When it comes to evaluating the resistance, leakage resistance of the insulator, we need to know the shape. And then basically, we define the differential element, dr on the surface, like this belt, for example, and then we integrate over the shape. And then we can obtain the resistance of the insulating layer, knowing the conductivity of the pollution layer. So that's usually done in computers. Mechanism of pollution flashover. How this happens? For the glass insulator, it's usually like that. You have the region where the insulation is, and then you have two electrodes. This is very schematic. So there is certain contamination, and then this contamination is exposed to moisture, creating the path for leakage current. So it's shown here, some leakage current. So contamination is never even. So at some locations can be more salt, in another location less salt, when it's exposed to moisture, creating this kind of semiconducting substance. So you may have regions where the concentration is lower, the concentration is higher, and then it creates what is called dry bands. Just simply because of the difference in the resistance of certain layers, portion of layers, it leads then to redistribution of the potential, and the current at certain portions becomes higher or lower depending on the uniformity of this layer, and then the losses come to play. If losses becomes higher because of the local enhanced current, so this region is drying, right? So at some point, one of this dry band can dominate because of the drying, and then it's continuous drying, it's actually expanding that, and then at some point the difference between the areas of this band becomes so high that micro spark creates here, and then it's even accelerating drying because of the higher local losses. So then you have this expansion of these micro sparks may then connect and then create the full threshold. So that's the effect of this pollution layer. Yeah, how they characterize these pollutions. So basically what people do, take insulator from the string and wash it. Separately washing the bottom side, separately washing the top side. And then, yeah, dry not drying, but filtering this water and getting the residual, and then drying it and waiting. So there are two parameters for evaluating the pollution density. One is called equivalent salt deposit density. So this is more or less like for solvable pollutions, and non-solvable deposit density, NSDD and ESDD. Okay, that's the guy doing this job. Very kind of fantastic job, I would say, going around and washing insulators. Yeah, this is taken from the standard. There is a relation between the ESDD values, milligram per square centimeter, and NSDD values, milligram per square centimeter. So there is some kind of equivalent one can think about, and depending on the level of this, it's a classification. Very light pollution, everything below this line. Light, medium, heavy, very heavy. So that's how the standard classifies these things. So of course, if you go to the right, it's much more dangerous for the insulation. Yeah, one can think about this example here. So three types of insulators with different creepage distances because of different shaping. F12, F12D, and F12OP or something is called. The same level of strengths, but different different design. So for the basic one, F12, it's this. Then it's ESDD level and the critical threshold voltage field. So this is the one here. This one is just like that. It's extended surface, you see, but at high ESDD level, it doesn't wash itself. So that's why it goes down. For this one, it extended really, enhanced creepage distance, and then of course the strength goes up. So it depends on the shape. Then, yeah, depending on different locations, you may have different pollutions on the top of the bottom. This is for the desert pollution. It's some typically it's on the top or on the bottom, depending how the wind blows at different time of months and so on. Different type of insulators. I will not stop on that. It's just demonstration. There is a tool, insulator selection tool for selecting insulators for polluted conditions. And this is based on statistical variations of the probability of stresses and the strength which is provided by the insulators, and then you have the pollution severity, and you can select the number of insulators for given conditions, for given stresses, and for given pollution levels. So input data, measurement of pollution, distribution of pollution stress, pollution flashover performance, number of wetting events, location, and then insulated dimensioning. So that's how the tool look like, and we will use it for one of the projects. So basically you provide the stresses, some statistical requirements, altitude, how many years between the flashover events should we spend, pollution characteristics, how they are presented as a layer or another way, and then type of insulators, and then you run the tool, and then you will get the minimum and maximum statistical variations for the creepage distance, and then select an insulator gives you number of units for the given length to withstand the given level of voltage. So that will be the task for the project. Yeah, non-ceramic, that's you can look yourself. Silicon rubber performance. Yeah, this one thing I wanted to say. Special type of conditions appear in tropical areas, because then it's all about biological growth. In South Africa, for example, you have such things. Algae growing on the insulators, creating kind of, reducing the arcing distances and this kind of things. For example, here from Tanzania, you can see this kind of thing. In Sri Lanka, in tropical areas, you have some biological contaminations which are hardly removable, basically. Yeah, of this type. Again, it's all about wetting. If it comes to wetting, so it creates conductive passes, and then it's a trouble. And there is a technique which we developed some time ago, when one may have kind of fluorescence measurements to evaluate the performance of the contamination level. So you have a track like that, you just send a laser beam, and then you collect the reflected light, and then you put this in the spectrum like that, and then you decide what the contamination is, and what is the level, and so on. So there are techniques of doing these things. Yeah, I think that's all. That was very short time for the contamination part. Okay, no lecture tomorrow and no lecture next week, so only Fridays. On Friday, first lecture will be given by Munmo, or Yuriy. She will tell us about liquids, and then Andreas Kukler will take second lecture on transformer insulation. Yeah. So have a nice day then.